So, what is light? Well, light is just one a particular segment of spectrum of electromagnetic radiation. Now let me show you a sketch of how electromagnetic wave looks like. So it's a wave, I'll make a little diagram later on, which consists of crossed electric field, and the wave is, say, propagating in this direction, just like the waves on the surface of the water are moving. If you have, say, a boat leaving the port, then in its wake there are waves, right, that will propagate and eventually hit the shore. So electric field could have a form of wave, but with light, in addition to electric field, we also have crossed, perpendicular to it, magnetic field that is here colored in blue. And in free space, the light propagates with the highest possible speed with which anything can move or any information can be transmitted locally from one position in space and time to another. So the propagation velocity, and it's often denoted with lowercase c, is about 300,000 kilometers per second. As you know, we mentioned that before, right? When we were estimating how long it takes light produced by the sun at 150 million kilometers away from us, how long it takes that light to reach us here on Earth. Or the sun, or the sunlight reflected off the surface of the moon, how long it takes that light to travel 384,000 kilometers, which is the distance between, average distance between the moon and the Earth. Okay, so you already know that. So you can say, well, what is the electric field? Okay? Well, what is it? Well, it turns out it's a fact of nature that there are particles in nature that carry electric charge, and charged particles interact with each other via the electric force. There are two kinds of electric charge, which we arbitrarily call positive and negative. Okay? We could easily call them black and white. Okay? But the main point is that opposite charges attract each other with electrical force, which happens to vary with distance, just like the force of gravity, as 1 over the distance squared. So positive and negative charge would attract each other. And two like charges, say two positive charges, repel each other, again with a force that is proportional to 1 over the distance squared. So the way we understand this is that how they interact is that one charge produces electric field, a condition in space around it, and then when you place another charge in that field, then it experiences the force due to that first charge. Okay? So basically how you generate an electric field wave, what you have, say, in the broadcast antenna, a piece of wire, you have electrons, charges that are free to move in a metallic wire. They are driven at a particular frequency. Okay? And these charges actually then produce oscillating electric field that propagates through space with this speed. And that's, of course, propagation velocity in free space. So what is the magnetic field? Well, it turns out that moving charges produce also the magnetic field. which is a different day, and again, magnetic field is a source of magnetic force that charges can experience. Right? And the two are intimately related. They are in fact different manifestation of one and the same thing, which is the electromagnetic field. So again, if you have an antenna and you are driving the charges in it at a particular frequency, they are moving, they are producing, in addition to electric field, they are producing also magnetic field that is perpendicular to this electric field. It turns out that magnetic field can also be produced by another property of elementary particles. It turns out that particles like electrons, protons, and neutrons also have an intrinsic degree of freedom called spin. It shouldn't be confused with the idea that these particles are spinning. That's what people thought initially, but particles like electrons are point-like, and there is no point in saying that a point can spin, right? Because there is no point, doesn't have any kind of direction. It turned out that in addition to electric charge and mass, they also have this spin, intrinsic degree of freedom, and that there is a magnetic moment associated with that spin, just like tiny magnetic needle associated with an electron or proton or a neutron. And in magnetic materials, like in a piece of iron that has been magnetized, it turns out that actually it is the alignment of these magnetic moments of individual electrons that is responsible for the whole thing acting like a bulk magnet. So there are different sources of magnetic field, but electric and magnetic field are just different aspects of one and the same thing. And it was only close to the end of the 19th century through the work of two British scientists, Michael Faraday, who was a genius, self-educated experimentalist, and Maxwell, who was a highly trained theoretical physicist, that basically people realized that electric and magnetic field are just different aspects of one and the same thing. Moreover, that the light is just one special case of electromagnetic field. Okay, so let me make my Mickey Mouse version of this nice diagram, and I will concentrate only on the electric field. Okay, so I will just draw this envelope that connects the tips of electric field lines. And this wave is propagating. Electromagnetic waves are always propagating. Unlike the waves, say, on guitar string or piano string, they are actually standing waves where the two ends of the string are fixed, right? Here they are propagating with the speed of, in vacuum, of 300,000 kilometers per second. But what characterizes any wave is its wavelength. It's a distance between two successive troughs of the wave, maxima of the wave, or equivalently the distance between two successive troughs in the wave. So this is wavelength, and it is often denoted by a Greek letter lambda, which is a Greek version of Latin L. And lambda is, looks like this. Okay, so it's either the distance between two successive crests of the wave or the distance between two successive troughs of the wave. either one is equal to the wavelength. Now it turns out that, and I touched upon that when I asked the question why during the total lunar eclipse, why the moon appears to be red, right? Strictly speaking, one would argue that during the total lunar eclipse, the moon is in complete shadow of the Earth, which is much wider than the diameter of the moon. The diameter of the moon is about a quarter of the diameter of the Earth. So if it's complete shadow, we shouldn't be able to see it, but nevertheless we see it and it appears to be red. And I pointed out that the reason for that is that the Earth's atmosphere acts as a medium through which sunlight propagates, but different colors, different wavelengths, because as I'll describe in a moment, what we perceive as a color is a particular wavelength of light. Okay? And it turns out that the Earth's atmosphere bends red light, longer wavelengths, more than the shorter wavelengths. So it sort of focuses the red light to the surface of the moon, right? That light is reflected off the surface of the moon back into our eye, and we see, it looks to us that the moon is red during the total solar eclipse. So here again, this so-called refraction of light, when it propagates through a medium, is illustrated, right? And white light, once it passes through a medium like a glass prism, is decomposed into different components. Each component or each color corresponds to a particular wavelength.